Well, it's my pleasure to present Cliff Taubes, the first speaker of the afternoon, who will talk about compactness theorems and gauge theory.
Yeah, so this is going to be mostly a men talk. But let me start out. I couldn't make the dinner last night. This is, first of all, I first met Karen Institute. Maybe it was 1980, so it was 40 plus years ago. And I remember I could route about when I should look Karen up. Karen's office. It's wonderful. Dynamic interchange. Karen told me all these things, and I walked out and I realized I didn't understand anything. And I said, wow, I didn't understand any of that. And then, over a period of time, 6 months, 8 months, 9 months, 12 months, I started, oh, so that's what she meant. Oh, so that's what she meant. Oh. So I realized that I was about 8 to 12 months behind Karen in any given conversation. I put that in perspective. The late Sir Michael, the TA, I would have conversations with Sir Michael, and during the conversation, of course, he would talk the whole time, and I would sort of interject with something, but then I'd realize, oh wait, he said that a half hour ago. So by comparison, I was almost a year behind Karen, but only a half hour. So the other thing I want to relate to, especially to any young people who are watching, is some advice Karen gave me when I was young. And the advice was avoid responsibility as long as possible. Which I don't know if she's taken that advice herself or not. Anyway. Okay. So I'm going to talk about the past. One thing is you can't escape your past, which I'll tell a story about later. But so background is, Karen's one of the kind of founders of gauge theory, modern gauge theory, and now mathematical gauge theory. And she wrote 4 or 5 papers on connections with certain bounds on the curvature. And these formed really the foundational analysis for all the subsequent work. So Simon Donaldson had this brilliant idea to look at connections would solve this equation, which I'll describe momentarily as cutting out a finite dimensional manifold in some bigger space and viewing the manifold as a cohomology or homology cycle. And you pair it with cohomology, and you're going to get an invariant of a 4 manifold. And so the fact that it's a manifold and it has a orientation, of course, that was a breakthrough at the time, but in hindsight, it seemed that sort of was a natural development from things people had been thinking about. The truly difficult issue in sort of Donaldson's formulation of gauge theory, and then the subsequent work by Andreas Flohr, inventing Flohr homology, are the compactness question. If you're going to view something as a cycle, it has to be compactly supported to evaluate something on it. And compact supported not just by itself, but you have to think of 1 or 2 dimensional families of cycles. So this was so Karen's work really lies behind this whole development, even up to today. I mean, Peter Kronheim, Tom Rothwood talked at the ICM in 2018 about using gauge theories to do stuff. And there's a program in MSRI now using gauge theories to do stuff. So this is all kind of still hot topics, and we're talking now over 40 years hot Okay, so let me start with the background of what, what did Karen, what was the original problem? So the original problem back in the old days, golly, it's amazing, it's 4 years later, I'm still writing these same equations. Again, you young people, don't waste your 40 years goes by like that. You think you're young, and then one day you look in the mirror and you go, holy shit, what happened to me? So I'm going to look at compact four manifolds. Compact over it is principal bundle, and some group, but I'm going to take the group because it's the only group I know anything about, is SU2. Connection on that group. So connection locally looks like a one form with values in the Lie algebra of SU2. And you construct a curvature, which is a two form with values in the Lie algebra of SU2. Now, if it's a four manifold oriented Riemannian, then there's a Hodge star operator constructed from the metric, which maps two forms and a square is one. So we have self-dual two forms of the +1 eigenspace and minus self-dual. And the equations that Simon Donaldson looking at says that FA is equal to minus FA plus. Okay, so that's formally it looks like an equation that is, it's a first order nonlinear equation. Zero when you're looking at solutions of those equations. So those are the sort of formal structure of the equations. Now, the interesting thing about this is, if you want to say something about solution to equations, you need some a priori bound to even get started, because even if you look at a linear equation, if it's a linear equation and it's you don't put some bound on it, you can always rescale, right? So the bound comes from this. In 4 dimensions, there's up to a factor which I can't ever remember, but up to some pi's and stuff. And h, if you integrate over x and you look at the trace, well, the plus part, plus a squared. Let's put a minus sign here. So this is the plus part. And the minus part is putting a minus there. This is the characteristic class of your principal bundle. So up to a factor, this is like the first country eigenclass. And so if one of these is 0, say FA plus is 0, then you're getting a bound on the L2 norm of the curvature. So Karen's, so that's your control. That's your only control. Okay. So Karen asks the following question: is suppose I have an L2 bound on curvature if I have a connection. Now, what can I say about it? About the space. Set of A's. This property. Okay, so the question in this context is, can I say you want to know that the set is compact? Well, you sort of already have a problem because there's this gauge invariance that bundle has a group, infinite dimensional group of automorphisms, and the curvature, if this is zero, then acting by an automorphism, it's also zero. In fact, the norm, pointwise norm of the curvature is invariant under bundle automorphism. So you can't really talk about compactness of sequences of connections. The best you can do is look at their orbit space on the space of fluids. Because, I mean, you can always take a sequence of automorphisms that don't converge and act on a single connection, and you're not going to get a convergent subsequence. So the question is, if I have a sequence of connections with bounded curvature, such that the integral of FAN squared must make some bound. What can I say about, can I change them term-wise by an automorphism so there's some convergence? So can I change? Gauge transformation so that convergent subsequence. So that's really a question we want to ask. And Karen's theorem says yes, that this in fact happens. That if you have a sequence in 4 dimensions with L2 bound on the curvature, then you can change the sequence by a suitable set of automorphisms so that you can get convergence not on the whole manifold, but on the complement of a finite set of points. So the answer is yes, complement of a finite set of points. And I'll explain in a sense how this is proved in a second. So this is where we were in in the 1980s. And we had this really great theorem, and then this is sort of lies behind a lot of the gauge theory. Okay, how many questions about this? Okay, so let's fast forward. So let me now fast forward and kind of where convergence is now. So I just wanted to, we're going to come back to this in a minute. So the generalizations of the self-dual equation. So after the self-dual equations, and Donaldson's work and Floor's work, people started looking for other equations that had this property. And one thing you can do is you can add, well, thinking back to the talk before lunch, you can add Higgs fields, you can add other fields. So there's a sort of generalized self-dual equations, which Ed Wynn's name is attached to, I think, all of them, but they have this following schematic form. There's an auxiliary field, which I'll call psi. And so this is a quadratic expression, which we say called plus. So self-dual part, this is 0, and then psi obeys some kind of elliptic type equation. So this is a first order elliptic equation. And so there are various versions of this sort of schematic thing. Well, these Higgs equations that we heard about earlier, there's kind of a 2-dimensional version of this. And then there are 4-dimensional versions, which, so it's all sort of somebody Witten. So there's a Boffa-Witten equation and Kapustin-Witten equation and Seiberg-Witten equation. And so the question is, in these contexts, what can you say about convergence? If you have it, so if you want to use equations like this to define, invariance of 4 manifolds, or invariance of knots in 3 manifolds, or things like that. Again, you have to, the formal structure of solution spaces modulo automorphisms are compact, forms formally a cycle in some big high dimensional space. And then that cycle you want to think of as a homology class. That sort of formal structure exists in all these cases. And so then the question becomes, is your cycle compact? And if not, can you at least give a characterization of the non-compactness? Generalization. So general question is, are sequences, is there a compactness theorem? Well, not counts. Okay. So let's think a little bit about how we might prove Karen's theorem. So that's kind of the where we are now. In some of these cases, we have a kind of partial compactness theorem, and others we don't. But so I hope maybe I'll get a few minutes to talk about that. But let me go back to try to understand how one proves Karen's theorem, because even in this case, Karen's theorem still forms kind of the basic starting point for analyzing these. So you have to kind of understand Karen's theorem. So we start, so the idea, the basic idea here in Karen's theorem is that if I have a small ball in the manifold, so we have some small ball of radius r, and if I knew, so if the point is if the curvature in a ball is equal to 0, so in a ball, curvature being 0 says the connection is flat, and in a ball or any contractible set, that they're up to automorphism, there's a unique flat connection. So what you do is you work in a small ball, and what you expect, what you hope is that if the curvature in a ball is not 0, but approximately 0, namely small, it should be close to a flat connection. All right, so what we would do is we'd choose our unique flat connection, choose a connection A0, which is flat, and then we'd write the curvature of A as some operator, first order operator. So we write our connection A as a difference between a flat connection and our given one. And so then we could write the curvature, or the self-dual part of the curvature anyway, has formally the following form, dA plus part. Now, if we can put this guy orthogonal to the orbit of the gauge group, then this operator is an elliptic operator. So the idea here is if you work orthogonal to the gauge group, then the equation FA plus 0 becomes an elliptic equation. And this operator being elliptic is a first order operator. To say it's elliptic says is that if this nonlinearity isn't bad, then this norm will control that norm. All right, so that's the sort of basic idea. So so this is essentially Karen's theorem that says there's a number which is this, that if FA squared, if the integral of FA squared over some ball of radius r is less than some universal number, which I'll call mu, for Uhlenbeck's constant, okay? If it's less, and then there's an automorphism, then there exists an automorphism in the ball that writes your connection, does. So writes it at A0 plus A, where norm of A is small. So we look at the covariant derivative, A squared all is less than some universal constant times the integral of curvature. And then a Sobolev inequality tells you that this storm, if mu is small enough, this piece is O of mu squared, and in a sense it's insignificant relative to this piece. And so now you have control of your connection in a Hilbert space norm. So that's the basic thing. So what you have to do is you have a manifold, and you cover your manifold by balls so that in each ball, the integral is less than Uhlenbeck's constant. And then you get, if you have a sequence, you get convergence on each of those balls, and then you can glue them together to get convergence on the manifold. And the issue in 4 dimensions, this question of convergence on the complement of a point, is that you don't have any a priori control over the size of the ball, which you can have at Uhlenbeck. This Uhlenbeck bound. And so you might have some number of balls where along your sequence, the size of the balls gets smaller and smaller. So if I have any one fixed connection, there's always some covering by balls. And if I have a sequence, there might be some balls where you have to get really small to get to Uhlenbeck convergence. But if you have an initial bound on the total curvature, then you have a bound on the number of these balls. A number of these balls where this bad thing can happen is just be over mu. So the story is that there are some fixed number of balls, depending on B, that can go bad, so some finite number of points, and you're and that's the theorem. So now we can go to more complicated problems. So that's the background for everything. This is Uhlenbeck's theorem. But in a way we can't. So as I said, we have these kind of more complicated problems, which I'm going to say a little bit about in a minute. But these more complicated problems we can't escape. We can't escape from Karen's theorem. Okay, so the idea in these more complicated problems is they all have an important property. more complicated problems all have a more complicated. If you take that the operator dA in all of these problems, and you take the square of this operator, so that's now a second order elliptic equation, and this in all these cases implies it can be written as something like dA squared psi, where this is the trace Laplacian plus some action of the curvature, the self-dual curvature on one side, plus some Riemannian curvature on one side. So this is some Riemannian curvature. This is our self-dual curvature. And the nonlinearity there, where I wrote the sharp, that quadratic term, is chosen so that this, when you take the inner product with psi, so you take the pointwise inner product, you get an equation which is basically minus the Laplacian of psi squared over 2 plus some positive parts. And then this is that notation there is chosen so that this is equal to so get a nice inequality like that. And in fact, if you want to put a 1/2 here and add back 1/2 to the plus part of the curvature, you get this kind of wonderful inequality, and this is the key to making those equations work, is the second order inequality. So what you can do is you can integrate both sides over the manifold. So if we wanted to integrate both sides of this inequality, over the manifold, well, this term, integration by parts, that term is 0. And so what we get is we immediately get an L2 unbound. We get the covariant derivative plus a half, plus part of the curvature. Plus half of this quadratic term squared is less or equal to some constant which is universal times L2 norm. And so what that tells us is that if we had a sequence with bounded L2 norm, then we get a sequence like this. And in particular, we get a bound on the plus part of the curvature. And therefore, we get a bound on the whole curvature because we still have that characteristic class. This integral up to sine is minus and various pi's, which I might be getting wrong, upon Triagon number of the wonder. So again, if you have a L2 bound here, then you're in a situation where you have bounded curvature and you can invoke Karen's theorem. And you also, so you get a kind of a convergence of the connection. And if you have convergence of the connection, now you have convergence of the first derivatives of the psi, you have convergence of this. You can use the equation over here. You can differentiate the equation, you get convergence of the second derivatives and so on and so forth. So the key in these other problems is whether or not you have control over the L2 curvature of the psi. So that's the question. Can you have sequences where that diverges? Are there sequences? Is it the case where all sequences have that thing converge, or is it the case where you have sequences where this piece diverges? So this observation, actually a paper by Karen and I think your student, Jack Liardo, paper about this, right? And Tom North's student Ben Mars wrote a paper about this. So the question is always, you know, is it possible that we always have, in all cases, this is bounded. Now, in the case of the Seiberg-Witten equations, it turns out yes, because this is the fourth power of the curvature and fourth power dominates the second power. So we're okay. But in the more general cases, it turns out that there are sequences where you can have sequences of solutions where this in fact diverges, and then you have to figure out what to do. But again, I want to stress that Karen's work sort of forms the foundation of this thing. And I'm going to say a little bit about what happens when that diverges in a second, but I wanted to now make a kind of point about being how Karen's work, you can't escape your past.
Well, you can try.
That doesn't work either.
Well, I don't know. I've managed not to worry about compactness theorems ever since I started working on best of shits maps.
Okay. Well, let me tell you a story about trying to escape your past. It isn't a math story, but I thought I'd tell anyway. So my brother, when he was young, lived in New York City and owned a motorcycle. And, you know, one of these big, you know, motorcycles. And so you can't really park a motorcycle on the street because if you take up a parking space, people get really mad at you because you have this motorcycle in a big parking space. You can't park it kind of off the parking space because people might bump into it when you park. So you park it on the sidewalk, lock it to a lamppost, but that's actually against the law. So you get tickets on his motor. You come out twice a week, 3 times a week. There'd be a parking ticket on his motorcycle. You take the ticket, crumple it up, and throw it away. This happened for a number of years. Anyway, so then he moved to California, Santa Monica. He bought a house, he got married, he became civilized, basically. And so it came to pass that he had to move back to New York City, to New York. And he went to so you have to go to the, whatever it's called, DMV, the RMV, I don't know what they call it in New York, Registry of Motor Vehicles, right, to get a driver's license in New York. So the lady at the Registry of Motor Vehicles looks up his record and says, "Oh my God, Mr. Taubes, I'm afraid I can't give you a license until you pay off your parking tickets. You owe $10,000. My brother, who's always quick on his feet, says, "Oh, wait, that's another Gary Taubes." It was me. And the lady goes, she said, "I'm always getting mail from this guy or this guy." And the lady goes, "Well, I can see why that happens." And my brother says, "You can?" And she says, "Yeah, because it's amazing. He's got the same birthday and social security number." Actually, that happened to me also. So when I went to MSRI 10 years ago, I got a little money from MSRI. They took out California taxes, right? So, okay, so fine. I paid my tax in California, went back to Boston, Massachusetts. About 3 years later, I got a letter from the Franchise Tax Board. So in every other place, it's Department of Revenue, whatever. In California, it's the Franchise Tax Board, right? I got a letter from the Franchise Tax Board. You haven't filed your income tax for the year 2010. If you don't file it by December 31st, we're going to institute legal proceedings. And I'm thinking, wait a minute, I paid my taxes. You know, what is this? Why do I have to file a tax return? And it says at the bottom, if you have any questions, call this number. I called the number, there's a lady answered the phone, and her name was Maggie or something. She said, "What can I do for you?" I said, "Well, you know, I paid my taxes. Why do I have to file an income tax?" It doesn't matter, you have to file an income tax. I'm like, "Oh, this is insane. What?" I said, "Well, okay, what happens if I don't file my income tax? I live in Massachusetts. You know, what can you do? She goes, well, she says, Mr. Taubes, she says, we can repossess your house. So, you can do that? She goes, we can do anything we wanted. So, so Rick, you know about TikTok. Maybe
I pay my taxes.
maybe you're so wealthy, wealthy people, they have accounts. You don't, California tax return is the tax return from hell. It was designed, I don't know if any of you guys lived in California, it was designed by somebody who flunked third grade arithmetic. Who's now getting revenge on everything. All right. So what happens? So we have to think of a sequence. What happens to a sequence? So I went to Stanford 3 years. Money. I was so scared in California that I said, okay, well, deduct a lot of money. I said, okay, you have to tell them how much to deduct each month. I made sure they deducted a lot. So be in trouble, right? So deduct a lot of money, and so this amount. And I got my first paycheck from Stanford. It's $0. I go to the office, the math office. I said, what happened? I didn't think I didn't deduct all of it. Then I looked closely. They were paying me. I was telling them the deduction. I thought it was a monthly check, but it was a bi-weekly check. So basically, I deducted the full amount. It was double. I was getting paid twice as much as I actually was. So I ended up for 3 months at Stanford or something, $0, and all this money went to the California. Stanford thought I was an idiot. How can you be so stupid? All right. So what happens? What we do is this. Well, the obvious thing to do, if we call this number R, or R squared, we just renormalize. And if you renormalize, and write everything in terms of R, the equations, the psi equation, the second equation is homogeneous. So, so you get an equation that says FA plus minus R to the minus 2 and you have this homogeneous equation, so that doesn't affect this. And so what happens is, or it changes this to minus Laplace and phi squared. And here is R squared. And here there's a 1 over R squared. Okay, so when you integrate this, and what happens is if you get a 1 over R squared here, and you get R squared here, and all these become phis. And this becomes a 1. And so what you get is you get some kind of convergence if you have a sequence. And it's converging. So this thing, so you have a sequence where the R's are going to infinity now. So you're getting more and more control over this is uniformly bounded. This quadratic term is going to 0 because it's getting an R squared in front of it. And you're getting less and less control over the curvature because that's a 1 over R squared. And so what happens with the sequence is this. What tends to happen with the sequence is that you get a limit. If I have a sequence of ANs and we'll call them phi ns now, we'll call them psi ns, and the RNs go to infinity, then again, by choosing automorphisms and subsequences, you can arrange the following thing: that sitting inside your manifold X, there's a subset we'll call Z. And Z is it has Hausdorff codimension 2. So, and it's so my student Boyer Zhang it has a finite two-dimensional codimension 2 Hausdorff measure. So it's two-dimensional submanifold. It's rectifiable, and you get convergence away from it. Okay. So in the original case with the self-dual equations, you got convergence away from a finite set of points. Here there's a Z, and this Z is characterized. So what happens is that the phi ns converge in a suitable sense. The ANs are converging. So this is ANs converge away from Z. Well, I'm being a little bit sloppy here. It sort of depends on which equation you're taking. This sharp term, but morally the story is you get some Z, which is codimension 2, you get convergence away from Z, and the norm of this limit extends, so this extends over Z, where it's equal to 0. So in fact, it's continuous, extends continuously, and actually in the Holder norm. So it's kind of an interesting, I don't know what you want to call it, free boundary problem in a way, is that the Z is determined by the norm of the limit. So that where the norm of the limit is, it goes to 0 is your Z, and you get convergence away from it, and you might not get convergence near it, but in any event, this phi infinity obeys a nice equation. Obeys an elliptic equation in the complement. So that's kind of morally what's going to happen. That's kind of a first approximation of what's going to happen for these other equations. Okay, so I think I'll stop here. Question?
You do mean Hausdorff codimension 4.
4 dimensions. Yeah, it's 4 dimensions. If you do it in 3 dimensions, then it's always codimension 2.
Oh.
Yeah, let me explain why it's codimension 2.
Yeah, I know.
You can actually see this. So this is an elliptic equation. Saying a linear combination, some matrix times. So these sigmas are sort of a symbol. And then you have derivatives. So it can't be codimension 1 because if why can't it be codimension? Because then 2 of these would be 0. 2 directions would be 0. Then the third one would be 0.
Oh, I see.
So you know it has to be codimension 2. So, but this is in 3 dimensions and 4 dimensions. So if just one of them were zero, so if this is the derivative, if this were the derivative along z, this one would be zero. And then the others, then you'd have, let's see. If you had codimension one, then these you could take to be the derivatives along z. I mean, this is, you know, an approximation because z is, you know, kind of rough, but morally, if you had codimension one, you'd have three of these directions along z, which were zero, which would tell you the fourth one was zero, and then so it has to be at least codimension. But that's sort of more like.
Do we know anything more about the structure of Z other than it's rectifiable? Because in minimal surface theory, people are always trying to prove a little more about its structure.
No, we'd love to prove more, but right now, in general, so here's a conjecture. Conjectures for generic metric, it's, you know, I don't know, C1, C2, smooth. One would hope. So we have singularity models. We know there are cases where it can't, at least locally in R3, we have examples where you know, it has singularities, and but I think a reasonable conjecture is that it's C1 or C2 or maybe even smooth for generic metric.
Okay.
I had a question that was the Penny's question. I mean, in a lot of the applications, you actually don't care what the metric is. I mean, there's.
Yeah, right.
Right. And so has anybody ever tried to actually look at some interconnection between the metric to get a better result by using the fact that the metric is important
That's what you would hope.
hypothesis?
Yeah.
So,
So you would hope to be able to prove some kind of if the metric was suitably generic. You also have to consider one parameter families of metrics.
yeah, sure.
So that's what you'd like to say. So I think the conjecture would be, first of all, for generic metric, Z is an embedded curve of some differentiability, and then for one parameter families, maybe you have that, or maybe it just has a cross. In a simple thing.
Well, I've also, I mean, yeah, I have to admit that I relapse every once in a while and think about this problem.
Yeah.
But you want to think maybe if you actually put a relationship between of the metric and the
And a solution.
yeah. I mean, in other words, of course, you make a
Yeah.
more complicated equation, but maybe that would give you.
That's a possibility.
You could pass the problems under to choice of metric rather
Yeah.
than.
So I'll have to go home and wait 12 months. And then perhaps I'll be able to answer your questions. But yeah, sure. That's
Can I embarrass myself by trying to throw a wrench into this? So for the scalar equation, the nodal set, I think Hart and Simon proved in the late 70s that you get codimension 2 singularities in the nodal set, but here you've got a system. So can the Hart-Simon thing be applied to push the dimension of the singular set of this nodal set, Z, down a little further?
Yeah, I mean, one would ideally that this should be, one would like the same kind of theory.
Yeah.
So the analog would be, you know, looking at singularities of eigenvalues, right? Eigenfunctions and stuff like that. So those are the theorems one would like to prove in this case.
I was hoping you could push it down to codimension 4, the singular set of the nodal set. Codimension 4, it's so codimension 2, I think, in the. Anyway, let me leave it at that before I embarrass myself. Maybe push it down one more, that the singular set is one dimension lower than the.
Yeah, it might be. I don't know. I mean, but those are the kinds of theorems we would want to prove.
Yeah.
Any other questions? So let me remind you that we'll go out immediately and take a picture, and then let's say the next talk starts at 25:03, I guess, and let's thank Cliff again.